Recording?
Yeah.
Okay. That was a great presentation by Sean Cross. Now I'm going to introduce to you Corey Geisner. He will be actually talking about the steam ejector experiment. He did pass out everyone handouts, so make sure you got your handout, so it'd be better to follow along with his presentation.
All right, Corey Geisner, I'm doing experiment 1, which is going to be the steam ejector. All right, so to start off, here's the experiment objectives. We're going to calculate the steam flow rate through a choke nozzle, investigate the efficiency of the ejector when used as a feed water heater, investigate the efficiency of the ejector when used as a pump, and perform an overall conservation of mass and energy in the system. First of all, what is a steam ejector? Steam ejector is a converging diverging nozzle that entrains a secondary fluid. So basically what it does is it utilizes a working fluid and the Venturi effect to pump a fluid from a lower pressure to a higher pressure. Alright, there's two different types. You have a subsonic ejector. Basically in a subsonic ejector, you have low velocity, high pressure steam coming in, and the converging nozzle, the area decreases, so it accelerates the velocity of the steam and also lowers the pressure. Your lowest pressure is going to be at the throat, which is the smallest area cross-section of the CD nozzle. So what you do is you place a suction inlet in the throat. And what happens is when the high velocity, low pressure steam passes over the throat, it creates a suction. That way you can utilize this as a vacuum pump. It then will discharge the secondary gas or fluid through the diffuser, so it expels it at a low velocity and approximately the ambient or exit pressure. How do you go back? All right. Then you have a supersonic ejector. Basically, what happens with the supersonic ejector is you have your steam coming in, your working fluid, that is then accelerated to a speed of Mach 1 in the throat, and then it comes out of the diffuser, and then it continues to accelerate, and then which is expelled into a suction tank. What happens is you have high velocity steam coming out, and you have a passage at the bottom of the suction tank. And as this high velocity steam passes over the passage, it creates a suction. And this is how you can use it to pump water. And then the water, or whatever you're pumping, is then going to mix with the steam and be expelled out of the exit throat of the suction tank. This is what our experiment is going to utilize. It's going to be a supersonic ejector with a suction tank. Here's the flow regimes for your nozzles. If you look over here, you have a subsonic. So basically what it's saying is in your converging nozzle, your Mach number is going to be less than 1, and also your diffuser. Whereas with your supersonic, as your nozzle converges, the speed approaches Mach 1, and the diffuser, as it leaves the throat, it's going to accelerate past Mach 1. Ejector operations, basically, you want to vary your upstream pressure. What that's going to do is change the velocities in the CD nozzle. So the higher your upstream pressure, you're going to have a higher throat velocity and a lower throat pressure. And then if you were to vary the downstream pressure, if you increase the downstream pressure, it's going to decrease your throat velocity. So it's going to have a negative effect of what would happen if you increase the upstream pressure, which makes sense. The inlet, outlet, and throat diameters will also have an effect on this because you use the diameters to calculate your Mach numbers, the ratios and everything. And also, you can assume choke flow in these conditions, which if you have choke flow, that means you achieve Mach 1 in the throat. A subsonic ejector, the throat is your pump. And a supersonic ejector, you have a suction tank after the CD nozzle. Here's a diagram of the apparatus, which I passed out to all y'all, which basically numbers all of the parts. So then, if you go to your experimental procedure, first you want to make sure the valve 13 is closed, which is the fill tank drain. Then you want to make sure that valve 14 is open, which is the delivery tank drain. Then opening valve 15, which is the supply. You want to fill tank 11 to approximately halfway. Open valve 10 to the delivery tank, to the ejector, which is object 12. Also open valve 9, which is the suction pipe, which is going to suck water from tank 11. Open valve 1 and adjust the steam supply to the ejector until water is drawn up through the ejector and discharged into the delivery tank. Then you can adjust valve 15 so that tank 11 is approximately constant. This way you can measure the flow rate. And then you can play with valve 9 and valves 1 and 10 to absorb their effects on the flow rate and how it affects the system. Here's the data that I used to calculate some experimental calculations. This was included on the lab handout. It gives us the diameters and the exit pressure and all that. Experimental calculations, this is what I used to calculate the Mach number upstream in the convergent nozzle. A is going to be your upstream nozzle area. A critical, which is the star, is your throat area. I've come up with an upstream Mach number of 0.037, which should be right because you should have a Mach number of less than 1 in the convergent nozzle. Then the next thing, I calculated the speed of sound. I used 1.4, which is for an ideal gas, so that should be kind of skewed. And then I calculated from temperatures 403 Kelvin to 413, which is 130 and 140 degrees Celsius. Next thing, I calculated the mass flow rate. This could be slightly skewed because I calculated it as an ideal gas, but the reason I did not calculate it using the density is because I didn't know the quality of the steam, so I could not figure out the right density to make my calculations with. This brings me to my final one. So why would we use a steam injector? We can use it to remove waste fluid from reservoirs using excess steam. It used to be to pump a fluid that also needs to be heated, and use it to pump a fluid mixture that needs to be heated and combined with water, and use it as a vacuum. That's it. Any questions?
What do you think would be more efficient to use it as a pump or as a heat stream?
Well, it really depends on what you're trying to use it for and why are you using it as that application. Does your process have excess steam, so you're using a byproduct to use it as a pump, and you want your wastewater to be heated, or are you just trying to pump something? Also depends on the quality. So the efficiency is going to vary, how fast the steam's going through. So really, the operation that you're trying to perform it on. So your question was, is it more efficient to use as a pump or as a heater? Well, are you using a subsonic or a supersonic? So that's going to have effects on it too, because if you're using a subsonic, it's going to pump a lot more efficient than it's going to heat, whereas if you're using a supersonic, it's going to heat a lot better than it's going to pump, because you have more fluid being introduced in the suction tank. So you have a high volume of fluid coming into your suction tank, heating a small volume of suction water. Whereas if you use a subsonic, you're going to be introducing less heat to your suction because you have almost as much heat coming in as you have fluid being sucked up, since you're doing it in the throat. So you have a small amount of fluid coming in both from the suction and the inlet of the nozzle. So you don't have as much heat to distribute, whereas if you use the supersonic, you have more fluid with less suction fluid, so it's going to heat more efficiently. Does that answer the question?